subject. He'll give his own set of topics having to do with black holes. But it's clearly appropriate for Gary, who is one of the pioneers in the modern approach to black holes. And we just saw how he and Stephen Hawking gave the derivation of the black hole temperature that we all understand very easily, and many other contributions. So it's great to have him here for the first time, I gather, at the Winter School. And he will give a series of lectures on black holes starting now.
Thank you, David. It's a great privilege to be here. Before I start, I want to, in a sense, apologize. This is going to be a very low-level course in black holes, where I attempt to show you how the classical theory and maybe some of the quantum theory works out, because I suspect many people haven't really seen this in the detail which people who understand relativity, general relativity, might like. I'm going to take a slightly historical trend. It won't be totally historical. And the first thing I have to say is if I miss out names, that's not deliberate. It's just my failing memory. Or no room on the overheads. I'm not trying to assign credit or other things at this stage. Most of what I will say will be restricted to the spherically symmetric case, because as soon as you get rotating, things get complicated. And I'm going to give most of the initial part of this lecture on the overheads. I had anticipated having more space for little diagrams, so at some stage I may have to lift the screen and draw some diagrams. I haven't got a list of topics in order. I'm just going to go through as the subject kind of developed. There will, of course, be jumps forwards and backwards. Any relativist is allowed a closed time-like curve every now and again. I hope you'll give me some feedback, tell me to slow down or whatever, or speed up. I want to start with a bit of prehistory, which is quite interesting and has its ironies. So in 1676, Römer measured or obtained a value for the speed of light. That was an interesting time, because from that time onwards, there was a theory, not necessarily a valid theory, which combined G and C. There ought to be such a theory. And at that time, the favored theory was what's called the corpuscular theory, which opposed the unfavored theory, which was Huygens' undulatory theory. Now, the Newtonians, mainly located but not exclusively in Cambridge, but also with the representation in France, as we shall see, and in Germany, took the view that light was the manifestation of light was the transmission of particles, corpuscles, which carried energy and momentum, and which, like all particles known at that time, suffered the effects of gravity. So there are two immediate deductions which were made early on, one of which is light bending. In 1784, in unpublished work, because most of his work was unpublished, Henry Cavendish, of whom I'll say a little bit later, derived this formula for the deflection of a corpuscle of light passing a massive object of mass m for large separations.
You mean with B minus 1?
B inverse. Thank you. Yeah. Yeah, that's right. Well, B could be the inverse of R, but... So that's the first deduction. It was also made independently by Soldner in the early 19th century. Cavendish had a friend called Mitchell. He's not well known nowadays, but some historians regard him as the greatest physicist in England, at least, between Newton and Faraday, or Newton and Maxwell maybe. It was apparent to him that there would also be the phenomenon of escape velocity, and thus invisible bodies. And just equating the escape velocity of sound squared, given by this formula, right? So this is a very familiar formula. So that if, I apologize, these overheads were made hurriedly, if r is less than 2 gm, capital M obviously there, which we now call the Schwarzschild radius, then it should be the case that particles couldn't escape. And so it gave rise to speculations about dark bodies and similar things. In fact, Laplace took this over a bit later, not acknowledging Mitchell. It's not clear whether it was an independent discovery. And they worked out, roughly speaking, that if you had a body of the same density as the Sun but about 500 times as large, this number would be sufficiently large that it would be invisible. So this is where this theory enters the subject. But of course, further progress was somewhat curtailed by the experiments of Thomas Young in 1810, I think that's right, on the interference of light, which then gave support to Huygens theory, and of course led, as we all know, to the development of ether theory and attempts to understand how light propagated in the vacuum. Now, basically speaking, the 19th century physicists made little progress in developing a theory of these effects. And these early ideas were forgotten. Indeed, they only really surfaced much later, after the discovery or the invention of the notion of a black hole in the 70s. Before that, they were hardly known to historians and certainly not known to physicists. Now, I mentioned Maxwell earlier, and the interesting thing about Maxwell is he did think about gravity, and he came across a couple of puzzles which are still with us. They're resolved, of course, by general relativity, as we shall see. So the first thing Maxwell did in that famous paper where he invented the Maxwell equations, he actually wrote down a stress tensor for electromagnetism, with which most people here, I expect, will be familiar. But he wrote one down for gravity as well, and as you can expect, it has the opposite sign to that of the Maxwell stress tensor. That looks all very fine, but of course what he wanted was a medium which was attractive rather than repulsive, and so that like charges should be attracted. And that was a puzzle to him. And even more was the puzzle that the medium, in the presence of gravity, the energy density of this ether, if you like, or this medium that was transmitting gravity, is negative and unbounded below. There's an enormous energy density and an enormous tension in the ether. That was about as far as they got, and there were speculations about how large that tension should be. So that's the setting pre-19th century, pre-20th century, and as we all know, this is the 100th anniversary of Einstein's theory formulated in terms of Einstein's equations here. And the equations basically says, everybody knows, I'm sure in this room, that curvature, a certain measure of the curvature, the Ricci tensor minus a half the Ricci scalar times the metric, is proportional to the energy density. The factor of proportionality has some interest, because if you work out its dimensions, it has the dimensions of tensional force, and it doesn't depend on h bar. So it's one of these quantities which they could have invented early on, as soon as they knew about the velocity of light. There's something going on, there's a tension, and it's plausible actually, as I will indicate later, that actually the meaning of this tension is that c to the fourth over 4g, or maybe 2g, is plausibly the maximum force or tension allowed in nature, and I'll give some argument for that later. Of course, this was combined with light in Einstein-Maxwell theory. This is the stress tensor that goes on the right-hand side, and of course, as we all know, Einstein linearized the equations and obtained a light deflection, with B in the correct place now, which is twice the Newtonian value. And I'll comment on that twice later. And this was checked observationally by Eddington in 1919, using an eclipse of the sun, which led, of course, to enormous enthusiasm throughout the subject. And one of the themes I shall be making here is many discoveries were made in the years from 1915 through to 1926 or so, because this was the most exciting subject. And many of the seeds of the origins of the theory were present at that time. I'm also going to make a comment here, which is ahistorical, if you like, and that is that this theory is the simplest supergravity theory. You can add 2 gravitini and you get n equals 2 supergravity in dimension 4, and I'll be commenting on that significance later. But there's been a great deal of interest, as we all know, in finding black holes in supergravity theories, what their role is, and in higher dimensions. But the basic simplest theory, which is going to tell you how this works, is the n equals 2 supergravity theory. Okay. Now, the first solution of these equations was found remarkably early. This illustrates the theme that within a few months, people were making serious contributions to this subject, and this contribution is the so-called Schwarzschild solution, which was also found in a slightly more rigorous way by a student of Lorentz called Droste. So basically the difference between the 2 derivations is something that Schwarzschild, I think, substituted an ansatz into the Lagrangian and varied it, which we all know is not necessarily valid, and Droste did it the long way and the honest way. But it makes no difference in this particular case. The 2 solutions work out. And of course what we find is we recover the 18th century result here, that this metric is singular at the Schwarzschild radius, r equals 2gm, which works out, as probably everybody knows here, at about 3 kilometers for a mass the mass of the Sun. Now, it's true that this metric is singular, and I want to emphasize why it's singular. It may seem obvious, but the point is that a coordinate chart with a metric should have the components of that metric on the one hand bounded, and on the other hand invertible. That's what it takes to have a good coordinate system. And you see that this coordinate system fails in both regards, because the RR component is certainly unbounded, and the 0, 0 or TT component is vanishing. Actually, that's not a big problem, as we shall see. The determinant, interestingly enough, is not 0. So actually, I misspoke slightly there. I should have said that the boundedness condition really fails. However, if you work out the curvature, it's quite finite as you go through r equals 2m, and you find it actually only blows up at the origin. So that suggests that what we now call a coordinate, this is just a coordinate singularity. What?
In your metric, you should use small r. These small r square. Otherwise, students may get confused.
I'm sorry, I should use what square?
You should use lowercase r.
Oh, I'm going to use uppercase r for a reason. I know it's a slight confusion, but you're right.
In the same slide,
definition of Schwarzschild.
Yeah. But of course, that's the coordinate value is r equals 2gm over c squared. Okay. Now let me tell you why I've used the r. So you've given me an excuse, which is that there's a geometric definition of this r. The geometric definition is the area of a sphere is 4 pi r squared. And I shall tend to use that as I go on.
What does more rigorously mean?
Well, I just said he actually wrote down the field equations and solved them. I think it's true that Schwarzschild substituted an ansatz into the action. And by the way, that's not rigorous.
Yeah. Gary, what does it mean it was realized? When was it?
I think at this time, people just said that's just terrible and, we should cut the thing off.
Including Einstein?
I think Einstein was certainly puzzled about that. I mean, you'd have to go back and ask people. As far as I can see, my sense of the literature, it certainly is that it was believed that no such object could exist because it was so small.
The first one to realize it was a coordinate singularity, I think, was Lemaitre.
Well, Lemaitre later found coordinate systems which run through, and I'll come to that. I'm not trying to be exactly chronological in my presentation. I'm just bringing out the bits. But my understanding is that the initial reaction was there would be no such object. And I'll come to another comment along those lines. So I'll try and expand on that point. Now, in fact, the first person to find an appropriate coordinate system that we now use was Eddington. Eddington introduced this retarded time coordinate, which I'm going to call little u, in terms of which the metric takes this form. Now, this is r star. This is the optical distance. I'll say that more carefully later. And he wrote down this metric here. And this coordinate system is good over the entire range of u, and r can go all the way down to 0. The reason being that although that vanishes, there's an off-diagonal term in the determinant, and so the determinant is bounded and everybody is bounded. It doesn't matter that there is a 0 here, because this is in fact a light-like surface. The surface is not conormal, or if you like, it's a wave surface. Eddington realized that an object, at least some stages in his development, in his thinking, a falling object would pass through this completely freely and continue inwards to the curvature singularity at r equals 0. And he also realized that the same would apply to a star which lost its source of pressure support. And he also, I think around this time, people realized that once you were in, you couldn't get out. And the reason for that is that this is a light-like surface. So let's see, is there an eraser here? Rubber eraser.
Where did you put it?
Yeah, okay.
Behind the screen.
Oh, wait a minute. Okay. All right, there we go. So it's a light-like surface, and such a light-like surface is such that the light cone goes like this. And so if you're on a time like geodesic and you pass that, you can't go back. Now he realized something else, and the reason is interesting and has some relevance to some later considerations. This metric could be written in the following form. It could be written essentially with no approximation as flat space plus something which is actually solve the linearized Einstein equations. So the arithmetic goes like this. This is what you start with. You break it up. You take out that term, and then you reorganize this term, which is in fact the same term as flat space in these coordinates, but with a different time coordinate. And the different time coordinate is the one that comes earlier, given here. I just replace u by t minus r over c. Okay, so this has some interesting consequences. You see, once you've written it out in this way, you see that the integration constant in Einstein's equations is only present to order 1. It's linearized approximation. So what you can say is that this solution, although non-linear in quotation marks and non-perturbative in quotation marks, is actually its own linearized approximation. The reason for that I'll expand on shortly. But what it means is that whether or not you've got a solution of the linearized theory or the exact theory, that can be a matter of a gauge artifact. So you shouldn't necessarily assume that black holes are a nonlinear phenomenon. But it has another explanation or an interest. It does involve it involves this r star coordinate, which is an integral which involves, let's see, it involves the mass like this, right? So you're right that the nonlinearity is, but I mean, you've just introduced a parameter, if you like, here, which you then cancel. So it can be cancelled by local diffeomorphism. Okay. Actually, this is interesting because why did he do it? He didn't do it actually because he was concerned with gravitational collapse. He did it because there was a rival theory going around, a flat space theory, constructed by Whitehead, the famous Whitehead of Russell and Whitehead, who reformulated mathematical logic just beforehand. Whitehead was, in fact, he made his living teaching physics. He loved the Maxwell theory. He accepted special relativity, but what he couldn't take was a background which was dependent on circumstance. He wanted an absolute background. And so actually, in his theory, this was the ansatz made for the metric. And then he had to solve. Well, first of all, you have to solve the linearized Einstein equations. And it's pretty clear that this will work, you see, because this is just a solution of Laplace's equation. But why did he put the u's in? That's because he wanted a retarded solution. So his idea was that you would solve to get the metric, and thus to look at what the consequences were of the three classic tests. You'd solve the equations using retarded potentials. And that will turn out to have an interpretation later. This theory was a major rival for, with Einstein's theory until the late 60s, because the three classic tests were absolutely the same, gave exactly the same answers as Einstein's theory. So people say, well, what's the difference? Now, of course, there were aesthetic reasons for preferring the theory of Einstein. But if you were a hardcore Popperian, which I believe some might be in the audience, is that right? You'd have said, we can't tell the difference. Eventually, Cliff Will in the 60s showed that actually this violates various tests on tidal interactions between the moon. And nowadays we have a large number of tests which show that it's not viable. Okay, that's one interesting aspect of this. Now I want also to say something else which we deduce from this simple formula, and that is there is a difference here between the retarded time coordinate according to Minkowski space, the background, and the retarded time coordinate due to the physical space-time, which involves this R star. And what you will notice here is that they involve this quantity, the logarithm of the radius. And at large distances, therefore, not only do these always differ, they differ by infinitely large amounts. The causal structure of this Minkowski background is infinitely far away from the strictly Einsteinian conformal structure. And this suggests, at least to some people, I'm not going to take a side about this, but I just think people should be aware of this interesting point. And this is suggested by Penrose and others, that the construction of a gravitational S matrix may be problematic. Certainly you have to take into account this very slow fall-off. You see, you could also take the more optimistic view, to quote Bohr's famous remark in a different context, that the opposite of a great truth is also a great truth. Now, one of the things that David has asked me to do is to comment on how things change in higher dimension. And so here's my first comment on that. Let's go back to the Schwarzschild solution. It's quite clear, and it's true, that you can replace this by the gravitational potential in arbitrary dimensions. So this becomes a r to the d minus 2, where d is the spatial dimension. And that was first written down, in fact, by a guy called Tangolini in the 60s. So you just have to make that ordinary substitution. When you do that, the logarithm goes away, because the logarithm came from this integral. And you're going to get some power here. The point is that at large distances, this is falling off like 1 over r. So when you do the integration, you get a dr over r. In higher dimensions, it would be r to some power d minus 2, and that would be convergent. So the structure of infinity in higher dimensions is rather different. And that's shown up in detailed studies of the conformal structure at large distances at conformal infinity, which I'll comment on later. Okay. Now, roughly at that time, to reinforce that people made rapid progress with the subject, we learnt the following result, that the Schwarzschild solution is quite clearly the only spherically symmetric static solution. I mean, there's a bit of work to prove that, but that follows really from the work of Droster, I think, because he made the most general ansatz and showed you could get rid of the term you didn't want. So the Schwarzschild solution is a unique spherically symmetric static vacuum solution, but you can actually drop, as was shown by Birkhoff, and actually somebody else called Gibbons earlier than he, but the paper of Gibbons is not very well known, that it's the unique spherically symmetric vacuum solution of Einstein's equations, for which this quantity here is space, this radius is really a radius. Obviously inside the horizon, this is no longer giving you a time-like surface. So we're looking at the asymptotically flat bit for this, but the local solutions are still the same. So, but externally, spherical symmetry implies staticity. And this is, of course, physically because of the absence of gravitational waves. Gravitational waves are polarized, and there's no spherically symmetric polarization pattern that you can dream up on the sphere. It has a significance, however, later when one discusses gravitational collapse. It means that spherical gravitational collapse is very easily solvable, but aspherical gravitational collapse is almost impossible unless you have a good computer and good ability to program. So that's where it's coming into our story. Now, at that time and earlier, there was a great deal of discussion in the physics literature about the idea that you could have a smooth model for a particle with no singularities. We all know that the standard model for the electron at that time was just the Coulomb field, but that has divergent total energy. And so the question was raised by Van Mies and others, could you make a model of a particle in electrodynamics with finite total energy? And that later gave rise to Born-Infeld theory and so forth. And there is such a solution, which, however, is not completely non-singular. It has a jump in the derivative at the origin, but certainly has finite total energy. And that's been, over the past few years, been greatly used in string theory. Okay, but you can ask the same question, and people did very quickly, in gravity. Is there a solution of pure gravity, not necessarily spherically symmetric, which is like what we would now call a soliton? You twist it a little bit, and then is there a solution, and is it stable? Well, the answer is there are no solutions. And this held up progress in this subject for a long time, certainly in areas where people had a more rigorous viewpoint of things. I want to give a couple of proofs, and I'm giving these to introduce some notation. So how do we formulate this? Well, one formulation is as follows. We write the metric like this. So this is a function of the x variables. Nothing depends on the t variable, and this is just a metric which is a curved metric, which we want to be asymptotically flat. Now, globally static means that this is always positive, strictly positive. We don't want what happens in the Schwarzschild solution. And we don't care about the symmetries. And to say it's asymptotically flat is to say that the metric becomes, in a suitable coordinate system, the Kronecker delta plus terms of order 1 over r, as r goes to infinity. So we need to write out the field equations, and the field equations split into two simple equations. First of all, the Ricci tensor of this metric is a double gradient, or a Hessian, divided by v. And the second is that the Laplacian of v is 0, which of course also means that the Ricci scalar of r of the metric is 0. And this will arise in later work. Okay, so now we have one solution for this, which is v equals 1, and we want to know if there's another solution. And the proof is very elementary. We write v as 1 plus w. W is going to go to 0 at infinity, and w will also satisfy this equation. Now, if this were flat, you'd be able to do that from undergraduate physics because you multiply the Laplacian by w and integrate by parts. And that's exactly what you can do in this case. The formula for the Laplacian will allow you to integrate by parts. I won't write it down, it's very simple. And since this vanishes, this vanishes, and so what you get is this is going to vanish and the boundary term vanishes. And so what you find is that the Ricci tensor of the space is equal to 0, which means also that this combination, Sij equals Rij minus a quarter Rij, R times Gij is equal to 0, because the trace vanishes. And now the point is, in 3 dimensions, there's no difference really between the Ricci tensor and the Riemann tensor. The Ricci tensor is given entirely in terms of the Riemann tensor, and conversely. And so what this means is that the Ricci tensor of this space is going to vanish. And so that means that you can find coordinates in which it's flat. This is a unique statement in 3 dimensions. And it's telling us that the vacuum is unique, if you want to use the jargon of quantum field theory. And there are no solitons. Now, you may ask yourself, well, firstly, you can prove it by a number of different ways. I'll give some different proofs because I'm going to introduce slightly different notation.
The boundary term is not so clear. The gradient of W is 1 over
In the end, it works.
It's probably using the possibility of the mass.
Well, I don't use that, but that's an alternative proof I was going to come to. Yeah. In fact, I think, let's see, there should be a W here. That's why it works. I beg your pardon. There's a typo on there. Overheads. Okay. My apologies. I mean, another way is to use the maximum principle. If there were such a function W, it'd have to have a local maximum, but it can't do. Okay. So, I mean, virtually every technique you've been taught will work. In fact, it also works in the stationary case, although I won't give the full argument. And that was given later by various people, including Linearized. I don't think he was the first, but there was a literature in the 30s on this. I'd like to present a slightly different way of doing the same thing, because I'll be using the notation later on, not just because I want to show off I know lots of proofs. So you could rewrite the metric in this form, and this form I find quite convenient. I rescale the spatial metric, and this quantity u should be thought of as the Newtonian potential. It really at linearized level does the same job, but it also at non-linearized level it sort of does the same job. Okay, so again we have to write out the field equations, and here is an interesting echo of Maxwell, because what we find is that the Einstein tensor of this rescaled metric gamma is equal to the Newtonian stress tensor of the function u. And from that it follows, or from the field equations, that this is again harmonic. And so you basically do the same thing. Now, there's yet another way of doing it. So this proof makes, it proceeds more or less as before, but there are other ways. The other thing is, of course, that this way of doing it actually explains that missing factor of 2 that I mentioned earlier. That missing factor of 2 comes because, you see, there are different ways of explaining this, but at first the point is that you've got here this term in the metric component G0, but you've also got this term here. You've got spatial curvature as well as just the effects of a potential. And they're completely equal in dimension 4, space-time dimension 4, so you double up on that 18th century value. Now, in higher dimensions, this becomes, to make the thing work nicely, 1 over d minus 2, where d is the spatial dimension. And so, in fact, you don't get quite the same balance, but you get the same equations of motion. Okay, so this statement works in more or less higher dimensions. Now, you can repeat these statements, and in fact, we'll see a slicker one, but it does have an application to modern-day concerns. So the statement is that in modern language, there are no fuzzballs in 4 dimensions. Now, these are vacuum fuzzballs, but the arguments I've given can be generalized to virtually all of the supergravity models. And the supergravity models I have in mind are the ones that Herman spoke of in his lecture. They typically consist of a bunch of scalar fields, a bunch of abelian vector fields, and that's it. It's a theory really of massless scalar fields, and very similar arguments show that this doesn't work. But you do notice that what we used was the result that a 3-dimensional Ricci flat manifold has to be flat. That is not true in higher dimensions. So you may have a concern that there could be fuzzballs in higher dimensions. And the answer to that is as follows. Firstly, if it's pure vacuum, then it is known from the positive energy or positive action theorems that the only solution is flat Euclidean space. On the other hand, if you have material sources, then you can in principle evade this, but only if you have fluxes. And so the 5-dimensional solutions, which are the only known non-singular solutions used in people who work on the fuzzball conjecture, people in addition to the original originators, people like Nick Warner and so forth, always have those features. So there are asymptotically flat solitons in higher dimensions, but you need a lot of machinery to make it work. That means that one can ask the following question. In that program, the idea is that there are so many of these solutions that we can account for the entropy of black holes, the number of microstates. The number of microstates being idealized as classical states with no horizon. And the question that you might want to ask yourself, if it's such a good idea in 5 dimensions, why doesn't it work in 4 dimensions? Makes me skeptical. But anyhow, that's a thought. Nowadays, as Juan implied, you can prove this very much more easily in a very simple step. What you do is you just integrate the Laplace equation like this over this manifold and assume there's no interior boundary or other infinity. And when you do so, you find that this volume integral, this bulk integral, is 0, but this would be the mass, and therefore the mass has to be 0. It has to be the ADM mass here, and according to the positive mass theorem, that means it's got to be flat. Now, I will give a proof of the positive mass theorem in this context later on in the lectures for those that haven't seen it. But it is a basic fact that if you have a initial manifold, if you like, spatial manifold, whose Ricci scalar is non-negative, then if the mass is 0, then it's got to be flat. And in general, the mass will be positive. This is, of course, an expected result, and is indeed, it should resolve the doubts of Maxwell, because what it's saying is, in general relativity, the issue of arbitrarily large negative energies is not an issue. It could be an issue in modifications of general relativity. It's certainly an issue in Newtonian mechanics, but it is not an issue in general relativity, modulo the fact that we have black holes. Now, if you have black holes present, there's obviously going to be a boundary term coming in this formula. And the boundary term can be written as twice kappa times A, where A is the area and kappa is the surface gravity. And that's because if you look at the boundary conditions, that you'd need for a black hole, they turn out to be, just by computing curvatures, so the black hole is located on the surface V equals 0, and kappa is the modulus of this gradient, and so in fact, when the modulus of this gradient cancels out from the integral, so you just get the area. And so this gives you the first of what are called the SMAR relations. And the SMAR relations are meant to resemble what can happen in more complicated cases, but also they're meant to resemble what can happen in thermodynamics. And I'll come to that later when I say something about thermodynamics, but it won't be in this lecture. Okay, now you can look at this and take a variation. The easiest way of taking the variation is to use some dimensional analysis. It's a bit like a Schwarzschild, but you know, how can one avoid imitating a great scientist like Schwarzschild? You have to be a little bit careful, but anyhow, if you do that, you see that the whole thing is going to scale. If you scale the area, you're going to scale the solution because there's a scaling symmetry to the vacuum Einstein equations. So making that scaling, you're going to find that you're going to get, so the area is of dimension 2 in length, and so that cancels the 2 and you find you get this formula. So this is a proof, if you like, in the simplest case of the first law of thermodynamics, where, sorry, that should be dA, excuse me, excuse me. I wrote these rather late at night, and without a printer to check. Okay, that should be dA, and there's some 2 pi missing, I'm afraid, or pi is missing. Let me get that straight for you because it is a bit confusing. The point is that A is 16 pi m squared, kappa is 1 over 4 m. I'm now putting C and G equals 0, and so dA is 32 pi m dm, and then, sorry, this is an 8 pi, excuse me. Sorry, no, that's right, that's 1 over 4m. And so I need an extra factor of 8 to get the formula that I want, which is dm is kappa over 8 pi m dA. Okay, so now you can ask for other solutions, other static solutions, and you might think that that's an absolutely hopeless task. You might think that there's no chance of making any real progress. But very early on, and this again reinforces the fact that a lot of bright people jumped into the subject and made a lot of very interesting discoveries, it was realized that, by the way, is this that visible because of lights?
No, you have to turn on.
No, the light.
Light, he didn't. It's not remote.
Or is that better? I hope the rest has not been invisible. But okay. Okay. So what we can look at is static solutions which have an extra symmetry. And the extra symmetry is a rotational symmetry plus reflection in meridional planes. So these are called axisymmetric static. Now you notice there's no cross term between d phi and the other guys. So that's what it means to say it has that reflection symmetry. And really what you find is that field equations take a very simple form. So this is the ansatz for gamma. Note that I've gone into this way of looking at the metric in which I've conformally rescaled or via rescaled the spatial metric with precisely the right thing, because it makes for very simple formulae. And what you find here is that, first of all, this has to be a harmonic function, but it's a harmonic function in flat, regular Euclidean space. That's not obvious, but it's true. But it's also remarkable, because the remaining equations give you the gradient of this factor here. Only those. Now, if I give you the z and rho gradient of a function, there's got to be mixed partial consistency. And the mixed partial consistency is simply that this equation is satisfied, the flat space Laplacian. So that's one of the miraculous discoveries made by Weil in the 20s. It actually forms the central core to all of the solution generating techniques and uniqueness theorems that we use in 4 dimensions. That and, did I mention the Kerr? I don't know that I did. The Kerr shorthand sense. But anyhow, So the question now you can ask is, how do you get the Schwarzschild solution out of this? Your naive guess would be to take a point particle potential for u. And that turns out to be wrong. It gives you a solution, but not one which is spherically symmetric, and not one which is non-singular. So this is quite a remarkable fact. And again, I'm mentioning it here because if you study this theory, this subject a bit more, you'll find that this construction is frequently used in more complicated cases. So what you find is that u, the correct solution, which you get from Schwarzschild, is the Newtonian potential of a uniform rod of mass m. Now the easy way to discover that is to do the coordinate transformation that I give down here, which is kind of the natural thing that you'd want to do. But anyhow, if you make that substitution, that's what you find. Now you may not know what the Newtonian potential of a uniform rod is, so I'm going to give the answer, and the answer depends on two distances. So let me see, what did I do with this? Here's the axis of symmetry. Here's the rod, whose mass per unit length is 1/2. And here is rho, and here is z. So again, it's like doing freshman, well, not quite freshman physics. But. And so we define R1 and R2, and the length of this is 2m. And the mass is m. Okay? Now, something is obviously going to go wrong here, or is it? So then you take the logarithm of this lot, and that will give you... So if you take the logarithm, of course, what it means is that when you take the e to the u, you get this kind of factor here. And what you see is that when the sum of these guys is equal to 2m, then this e to the 2u is going to vanish. And so what that means is that this is the horizon. Now what you can also do is say, well, what about the r equals constant surfaces? There's something a bit peculiar happening here. And the answer is that what we can do is we can erect elliptical coordinates like this. After all, if you wanted to solve this problem and you've taken an electromagnetism course, find the electrostatic field due to a uniform charge source, the first thing you'd do is open a book on special coordinate systems, and you would find that you could actually solve for this guy. And here are the explicit formulae.
Because the source, if you want, has no quadrupole moment.
I think it has a... Doesn't it have a quadrupole moment in these coordinates? I think it's coordinate dependent, you see, because basically these ellipses map to r equals constant surfaces. Another way, of course, of looking at this is what Weil probably did to figure this out was to take the Schwarzschild solution and perform a conformal map. Okay? And so that's the phenomenon. But this is actually not uninteresting. Suppose now, because we've got a linear equation, we can always superpose solutions. We start off with a linear equation, and then we find this k, but we're guaranteed we can always, in principle, find it, and some people are clever enough to find it. Now, one possible thing we could imagine now is that we took two rods, like that. And that's looking a bit dicey, because that's supposed to be a black hole, and that's supposed to be a black hole. But what's gone wrong here? Well, what's gone wrong is that if you look at this formula, unless k is actually 0 on the axis, you'll have a conical singularity. Okay, it'd be like a cosmic string. Now, k is given by a line integral. So you might start off from here, and then you integrate. Now, it doesn't change around. There is a change around here, which you can evaluate. It's the difference of the Newtonian potential. And then you get to here. Well, if it's 0 here, it won't be 0 here. So you've got a conical singularity between these two black holes. You can evaluate the energy momentum tensor on that conical singularity. And what you will find is that the force or tension is given by, well, in general, that's what you get. And so, in fact, you will always have a force between these guys. You cannot eliminate it. Now, this is part of a saga. There was a guy, Silberstein, in the 1930s, who wrote to Physical Review a short letter pointing out the existence of this solution and claiming the whole theory was inconsistent. And in the next issue, Einstein and Rosen pointed out that he'd forgotten about the conical singularity. At this stage, I want to say that actually, since physically you expect this deficit angle to be no bigger than 2 pi, you get this constraint on the tension, which I mentioned earlier. Of course, that tension, if you're a string theorist, has some relationship to the tension of string theory and might have alerted you in the 18th century to the existence of a theory with a fundamental tension. But that's why I believe it's a fundamental limit. Now, actually, that remains a conjecture. You can try it out on various cases. Basically, if you try to keeping apart two black holes, either with what is in the literature called a strut. So, if the conical singularity is here, then it would be called a strut, and here it would be called a string. And the point is that if you try to keep, if you just do a simple order of magnitude calculation, if you try to keep two black holes apart in any way, you'll find that by the time the force between them has risen to this value, they're already inside a common event horizon. Recently, I've looked at this in a bit more detail, and there are arguments which I may have time to go over to say maybe I can change that factor by a factor of 2. You see, basically, it's based on the Gauss-Bonnet theorem, and I'm saying that I don't want to get a situation which is, that's the limiting situation, where the spatial metric would have a deficit of 2 pi. But actually, you can imagine, and there exist solutions for which it goes down here, and that would give you an extra 2 pi. I'm going to talk about those later. Okay. Now, what happens if you take a single semi-infinite rod? This is also an interesting question. So if you took a semi-infinite rod with, again, the same mass per unit length, you get a big horizon. What kind of horizon can that be? I can play this trick of asking the audience to tell me the answer. So anybody, any suggestions? Well, it's written down here. I'm sorry, sir. So either they're not reading or asleep. Okay, so this gives Rindler space. This is the acceleration horizon of Rindler space. More interestingly is to put another guy here. You still get a singularity, and that is what's called the symmetric, which has a much more complicated formula in local coordinates, but is easily constructed this way. And you can also do something a bit more interesting, which is to, as I will explain later, you can charge this up and charge this up, and then you can eliminate the conical singularity. And that actually gives you an instanton for the pair creation of charged black holes. So you see, this technique is very useful. That's why I'm mentioning it, not necessarily because it's a historical curiosity. Because once you get going with solutions which are as simple as this, you can then apply the technology of solution generating, which I will describe later, and get a whole bunch of more solutions.
This
would give you another bound, this half-infinite?
No, it's going to give you the same thing, you see, because the basic idea is I'm saying I don't want a conical defect with delta bigger than 2 pi. This one, which the other counterexample I mentioned, is more complicated. It's based on a solution where the stresses are actually continuous, Maxwell stresses, but also the topology is different. Yeah, I think that it's not really clear. Interestingly, this gives you another bound, of course, which is people talk about in gravitational radiation theory, which may be relevant indeed for an experiment, because there's something called the Dyson bound. Now, if you multiply a force by a velocity, you get the rate of doing work, and that will just involve a different power of c. That is believed by some, but not by Dyson, to be the largest possible luminosity in gravitational waves that an isolated source could have. When you asked Dyson, actually, he said, no, that's not what I said. And it's true, it's not what he said. What he actually said is that prefactor comes out front when I consider the orbiting motion of stars, how much radiation comes out, just the Landau-Lifshitz formula, if you like. If you determine that they're going around with a maximum speed, then it's a multiple of that number. But actually, Dyson at that stage was not interested in black holes. He was interested in interstellar communication. So it's totally irrelevant. But in honor of Dyson, it's now called the Dyson bound. Okay. Yeah? I'm going to come to that, but I could anticipate by telling you the answer. Okay? So you can indeed have 2 rods, let's say. And I said that you can apply solution generating techniques. In this context, I will put it in the context of Einstein-Maxwell theory. And there is a solution generating transformation, which is called a Harrison transformation. And what that can do, if you apply it to this solution, is to charge up these rods. And in general, if you do that, they acquire a charge to mass ratio which is equal. And this deficit angle is not going to be changed. But, well, the deficit angle will go, sorry, I didn't say that correctly. The deficit angle is essentially due to an integral along here. And so if this integral is non-zero, then you will still get it there. Okay, but a feature of this transformation, which is like a Lorentz transformation in a fictitious internal space, is that as you boost up, these get shorter and shorter. In the limit, when they go to 0, the charge to mass ratio goes to 1, and you obtain a special case of the so-called Majumdar-Papapetrou solution, which is the standard solution for 2 black holes in the axisymmetric case. And of course that works for arbitrary many of these things. For what it's worth, you can do the same thing with gravitational instantons and a whole lot of other stuff. You can, if you start with a theory which has some solution generated from rods, you can get the extreme ones by boosting. Okay. And this technology has been used a great deal in finding higher dimensional black holes and other more complicated black holes. So any more questions at this point? Was that a suitable answer? Okay. So what can we conclude? We can conclude that by the mid-1920s, or maybe even into the 30s, lots of the material was in place to study spherically symmetric gravitational collapse and so forth. But it didn't happen. And so you can ask why it didn't happen. And I think it didn't happen for 2 separate reasons. It didn't happen until 1939. I think there were 2 reasons. The first reason was that quantum mechanics intervened and everybody wanted to work on quantum mechanics. And the second reason was there was no urgent motivation for it, because nobody believed that objects of this sort could exist. That changed radically in the 1930s as a consequence of quantum mechanics. So I'm now going to explain how that works. I won't give all the details, but I'm going to introduce the players that cause people to think about this, which is, of course, white dwarfs and neutron stars, which I don't know if everybody knows the story. If they don't know, if everybody does, I'll pass on. Okay, so what is a white dwarf? Well, one of the most bright stars in the sky is Sirius, which is of great interest, of course, to ancient Egyptians. And in 1844, Bessel measured its proper motion and discovered it was in orbit around something else which he couldn't see. Eventually, that companion was observed in 1862 by an astronomer called Alvan Clark. It had a very low luminosity, so you can't see it with the naked eye, but a high surface temperature. Now, if you believe that it was emitting thermally, you can deduce the radius of the object just by simple dimensional analysis using the black body formula. And what you find is that this magic number, gm over c squared r, is about half times 10 to the minus 3. So that's a moderately large number compared with what it would be on the Sun, which in fact, this thing, you see, has, on the Earth rather, because this thing has a mass which is comparable with the solar mass. And so what you've really got is an object which is the mass of the Sun compressed within roughly an Earth radius. In fact, shortly afterwards, Eddington realized in 1924 that if this fact were true, there should be a significant redshift coming from that object. And he suggested to the astronomer Adams that he would try to measure it. I think that measurement is somewhat controversial. Some people believe it, some people don't. I think the establishment view now is it probably is observable. And so that led to a mystery about what was going on. This was highly dense matter. And in fact, in 1926, R.H. Fowler, who was a theoretical physicist in Cambridge, with research students such as Dirac and others, suggested that this high density was due to quantum degeneracy pressure. That is to say that the star had run out of energy and so was just supported by the pressure that keeps a mixture of electrons and protons apart. And in this particular case, the electrons would become degenerate first. And so you just thought of as the protons as passive stars, and they provided the pressure support due to the Pauli exclusion principle. Basically, the density of the protons would, well, we'll see in later. And then in the 1930s, 3 people worked on these white dwarfs. I think 3 suggest, or at least 2 suggested before Chandrasekhar, that there should be a maximum mass. And Chandrasekhar showed it with the full rigor at his disposal, that higher masses than about 1.4 solar masses, the electrons, basically become relativistic, and no stable solution would therefore exist. Now, by a curious coincidence, in 1932, Chadwick discovered the neutron. And Landau and Zwicky and Bader proposed the existence of neutron stars, which they thought could arise because the electron and the proton could inverse beta decay and form a degenerate gas of neutrons. But they also realized that the same arguments that were used for the instability of a white dwarf would also work for neutron stars with a critical mass which is about the same. Now, these bounds turn out to involve all 3 of the so-called fundamental constants. And so I think I would like just to go over the theory very briefly, if you'll forgive me, because I think you can call this the first non-trivial result in quantum gravity, although we don't normally think about that. So presumably a non-trivial result in quantum gravity is one which involves all 3 of the fundamental constants, which I've illustrated with this cube that people sometimes use. We normally think, quantum gravity is very sophisticated and complicated. But from the point of view of physical applications, this is the only one that we have great strength, great faith in understanding. I'm not therefore making statements about whether we need to quantize gravity or something. Of course, gravity is completely passive in this. So I'm just going to give you roughly a derivation of this result for those that haven't seen it. So, so in a non-relativistic gas, the energy density U, that's not retarded time, goes like the number of electrons per unit volume to the 5/3 power, and the gas has an equation of state which is roughly P equals 2 over 3U. When it becomes relativistic, the formula changes. I mean, you can check this from elementary stat mech, and it becomes, you get this P equals a third rho. So this guy is going like 1 over r to the 5, and this is like going 1 over r cubed. The crossover occurs when the electron number density is 1 per Compton wavelength cubed. Can't really be anything else. Now, a star will extremize, but not minimize, this potential energy. So this term is just this is a fudge factor of order unity, and this is a fudge factor of order unity. This goes like m squared over r, and this goes like the volume times the energy density. And the first term varies as 1 over r, and the second as 1 over r squared in the case of non-relativistic physics. And so there is a critical point. On the other hand, in the relativistic case, both goes as 1 over r, and there is no stable configuration. This, of course, is a very crude argument. Chandrasekhar wrote down the classical equations for pressure support, and actually it's now been proved pure mathematically by looking at the many-particle Schrödinger equation by various people, including Dyson and Lieb and people like that. So basically this is a problem in quantum mechanics. It's not often thought about that. Think of the multi-particle Schrödinger equation for electrons in a gravitating situation, and estimate the ground state. Now, if they're non-relativistic, there's no difficulty doing that, and the ground state energy scales as you would expect, and then you can see easily that there will be a stable configuration. When you do the non-relativistic case, you kind of fudge it, because you need to change p squared over 2m into some approximation which is going to be like the square root of p squared c squared plus m squared c to the fourth. But that they did, and with all the rigor that communications in mathematical physics demands, they showed that this is actually a true theorem in quantum mechanics. So that's why I think we could really...
1 over R4 in the second line.
Did I do something wrong? Excuse me.
Not to be confused here, 4, 1 over R4.
Oh, 1 over R4, excuse me. Yeah, I'm sorry. Yeah, you're absolutely right. You can actually estimate what these radii are, and the main point is that they're all basic multiples of the mass of the nucleon, m sub m, the Planck mass, and the mass of the electron. And so what you find is that for white dwarfs, Gm over r is going to be given by the ratio of the mass of the electron to the mass of the neutron. That's how it scales, not its precise value, which is 1 over 1836. So white dwarfs are moderately relativistic. They're more relativistic than the sun, for example, but it's a small factor. On the other hand, if it's neutrons that are doing the job, then this becomes of order unity, and a neutron star is like this. Now, I display these formulae because if you think about them, they are basically statements about what we now call the hierarchy problem, or Dirac calls the large numbers problem, because they only involve the ratio of the Planck mass to the masses of the standard model. So they also give rise, of course, to various anthropic arguments. In the case of neutron stars, I won't go through this argument, that inverse beta decay can take place. And historically, of course, pulsars were discovered by Hewish and Bell in 1967, and immediately people proposed that the pulsar, the one they saw, was a spinning neutron star. And in fact, in 1964, even earlier than that, the first X-ray source, which we now believe to be a black hole, was also identified. Okay. I want to remark at this stage that... What?
Where is quantum gravity?
Well, it's got h bar, it's got c, and it's got g. What the hell do you want more?
No, quantum meter gravity.
I'm not saying there are quantum fluctuations in the gravitational field, which is a different question.
H is just,
Well, it's zero temperature. Okay, the usual assumption is that the thing has got down to zero temperature. There's no thermal energy. It's lost its thermal energy. Actually, it wasn't quite hot, but the thermal energy is very small compared with the rest mass energy. So, I mean, these sorts of problems preoccupied Wheeler for a long time, and he talked about cold, fully catalyzed matter and tried to get the equation of state. Okay. I'm now going to make another, no doubt, provocative remark, but anyhow... the same, I hope it's provocative, the same statement, at the same time that this was going, well, a similar calculation has been done by Dickey, and I think it's a calculation everybody should know about. It's just an order of magnitude calculation, but he estimated the lifetime of a main sequence star. Of course, in terms of the same constants, and you get an answer. And that answer turns out to be roughly the Hubble time. So his response to Dirac's idea that we should change gravity by having a time-dependent gravitational field, an extra scalar or whatever, was that we could only measure the Hubble constant at such a time that stars had time to evolve, and therefore it was no accident. It wasn't a coincidence or something like that. So this is one of the earliest anthropic arguments. But what I want to draw your attention to is that we would now want also to understand things like the cosmological constant. And this suggests, I'm not going to talk about it in detail, people have speculated, but this suggests that there's some interesting link here. Why is the cosmological constant what it is? Well, a lower bound is provided by the Hubble time, but that lower bound is going to be provided by this combination of masses for the standard model particles. And so the question you could ask is, could that come out of some microscopic theory? For example, if we try to understand the renormalization group flow or something. I will not try to answer that question. I will just leave it as a homework. Well, the cosmological constant can't be too large. Yes, it provides... well, the universe wouldn't have lasted that long, right? It could be zero, so it's a weak argument. It's like like many of these anthropic arguments.
This calculation is completely wrong.
Good.
The lifetime of some stars on the main sequence is 10 million years.
Well,
It's much shorter than that.
yeah, they could be that low. Yes, that's right. But the ones that we're interested.
Not so much, it could be also infinitely long.
Okay.
So and there is a coincidence here that the Chandrasekhar mass by coincidence is comparable to the size of stars. It's just a pure coincidence. It's nothing to do with fundamental constant. The idea that the typical mass of stars is because of the Chandrasekhar mass is wrong.
Well, the calculation of the Chandrasekhar mass, I believe to be correct. If you're saying that we don't understand main sequence stars, I defer to you. Okay. So that brings us to a spherically symmetric collapse. And I want just to indicate how this works. So the first people to really look at this were Oppenheimer and Schneider. And they considered the gravitational collapse of a spherical ball of pressure-free fluid. So the idea here is the simplest thing you can do is if the collapse is due to the pressure giving out, let's put it equal to zero. Okay. And 5 minutes? Okay, that's okay. And so what they did was consider the following problem, which I'll discuss next time, but I'll just state the problem. We have a ball of fluid which is collapsing, and independently of whether the pressure is zero or not, we are blessed by the fact that we know the external metric completely. We know it cannot emit gravitational waves during the collapse, and we know the exact formula for the external metric. Now we also know that the boundary, if it's no pressure gradients, should be in free fall. And so it's in free fall as a geodesic, both of the internal metric and the external metric, which tells us that we don't actually need to know very much about the internal metric. I'll write down an internal metric next time. So these are the basic equations, and what we deduce is this familiar fact that the ball crosses r equals 2m in finite proper time, which is tau in this. But if you look at it in the large radius limit and measure it in terms of coordinate time t, then it takes an infinite time. It doesn't get to the horizon until little t goes to infinity. So that's the basic discovery they made. I'll elaborate on that in the next lecture. Let me just finish my remarks by saying that, in fact, it had been a long-standing conjecture for many years that a static star, from which we think we're starting off with, that's the crudest approximation, is spherically symmetric. And that's actually a theorem proved by these guys, using, I think, the positive mass theorem, as a matter of fact. Okay, so I'm going to stop my lecture at this point.
What year is Birchhoff's theorem?
Well, there's a student, I think he was a student, who proved it in 21. Birkhoff proved it in his book in 22. And no one mentions this guy until very recently, because they rediscovered the paper. But Birkhoff did not, as far as I know, give it an interpretation in terms of gravitational radiation. I mean, it's a relatively easy deduction from the field equations. Spherical symmetry. Exactly. And then what happens is that the cross Ricci tensor term RT, or GRT equals 0, gives you immediately that it's time independent. It's a very simple calculation. Every static perfect fluid, right? You might think that if it's gravitating, you know, it could be a pear shape, but that's not allowed.
Sphere.
Yeah, it's spherical. I'm sorry, I meant to say spherical. My apologies. Yeah, spherical.
Okay, so I suggest in 2-3 minutes that we are going outside cold. So in 2-3 minutes we go down. Don't want to stand outside the phone. This is the phone.